So we were talking about liquids, we talked about vapor pressure, right? And so remind me what vapor pressure is again. The pressure above a liquid in a closed container, right? So in any closed container, like the water bottle there or what have you, there's always some number of molecules in the gas phase, right? Those molecules are flying around, banging into the wall, so they're exerting a pressure. What happens to pressure as the temperature goes up? Pressure goes up, that's right. And then we said we can calculate that vapor pressure as a function of temperature, and that was our Clausius-Clapeyron equation, right? We said natural log P2 over P1 is equal to delta H over R multiplied by 1 over T1 minus 1 over T2, or you can put a minus sign and switch those ones and twos, right? That's what this blue curve is. If you look at this blue curve on this graph right here, the blue curve is the pressure versus temperature graph, and it's got that nice exponential to it. That's why we saw it written as natural log, because that made it make linear sense to us. So that blue curve is the liquid vapor coexistence curve is what that's called. Anywhere along that line, those temperatures and pressures both will exist. The liquid and the gas will both exist at that temperature pressure combination anywhere on the blue line, okay? Going across that blue line from, say, from here to there, well, that is a transition from liquid to gas, and what do we call that? Yeah, evaporation, vaporization, that works, right. Liquids do a weird thing, though. There's some pressure that we can get to and temperature, and we call this the critical temperature and the critical pressure. And at that point, the difference between liquids and gases go away, right? So what you're looking at on in the actual pictures up there is that's carbon dioxide, and that's a carbon dioxide along that line, that blue line. That's the liquid gas coexistence curve, and you can see when we're far away from that critical point, it's distinctly two phases. We can see the liquid there, we can see the vapor there. Well, we can't really see the vapor there because it's invisible. And then we are going to travel up that blue line closer and closer to that critical point. As we get close to that critical point, you can see that the phases are starting to look similar to each other, right? We're starting to see a little cloudiness in the vapor there, so it starts to look like fog maybe. And it's not a nice, crisp, clean liquid anymore either. It's kind of foggy there too. And then once we get to the critical point, and at any point past the critical point here, we call that a supercritical fluid. So a liquid and vapor doesn't exist anymore past that point, right? These things have really neat properties. So what's going on at the molecular level? Why do they exist? Well, we know that liquids exist because they have some intermolecular forces that hold them together, right? As we increase the temperature, we increase the energy in those molecules, and they can overcome those intermolecular forces, and so they should turn into a gas. But if we increase the pressure, we squeeze those particles close together again, and we make them interact with each other like they're a liquid. So that supercritical fluid range is something in between a liquid and a gas, because they got enough energy that they should be a gas, but they're squeezed together tight enough that they should be a liquid. And so they have weird properties that's somewhere in between a liquid and a gas, okay? And that's a supercritical fluid. And they use this stuff for lots of different things. It's actually used in some dry cleaning. They'll pass a supercritical fluid over dirty clothes, and it'll dissolve oils and things like that. They use it for decaffeinating teas and coffees. They pass supercritical CO2 over coffee beans or tea leaves. It will dissolve the caffeine in the CO2, and then all they have to do is change the temperature or pressure, and it goes back to non-critical, and all that stuff falls out of solution, right? So they have uses all over the place, but this is probably your first introduction to the concept of a supercritical fluid. And again, close together like a liquid, but they got enough kinetic energy to overcome those intermolecular forces. So you got this weird kind of foggy stuff going on up here. So again, that's called the critical point, and it's designated by the critical temperature and the critical pressure. All right, that is this particular one point here where the stuff ceases to be different. Okay, and then everything past that in this region up here is called a supercritical fluid. All right, so that's kind of the liquid gas boundary and what can happen there. So we get evaporation as we go across that. If we went this way, what would we call it? If we started at a gas and ended up over here to liquid, what would we call that? What? Condensation, for sure. Which one's exothermic? Condensation is exothermic. Why is it exothermic? That is the definition of exothermic. But why is it exothermic? Yes, together you're correct. Right? Together you're correct. Gases have more energy than liquids. So when you go back to a liquid, the energy has to go somewhere. Where does the energy go? It goes into the formation of those intermolecular force attractions, right? When those are created, energy is given off. That's how we remove the energy from the system. It's by the creation of those lower energy states, which are attractions.